doing calculating. Like we're not coming up to a number answer. So I want you to be thinking about when we get to our example, how this can relate to the word identities that you guys are doing. In the word identities, you had to go one word at a time, change one letter, one thing, and then you had to come up with a brand new word. Okay. What we're going to be doing today and Tuesday, Wednesday is either simplifying or verifying trig identities. And that means like taking an expression and changing the way that it looks, one step at a time, okay, by something that's true. We're not just going to make stuff up, of course. So we start with what are called fundamental trig identities. These things, I'll tell you, are things you should know for your quiz on Friday. Like they will not be provided for you, so you have to know what the substitutions allowed are. And we're going to start with the reciprocal identities. Okay. So we have 6 trig functions, and every trig function has a reciprocal, right? The reciprocal to sine is cosecant, and vice versa. The reciprocal to cosecant is sine. I would guess that you guys know the trig identities for the reciprocal trig functions, cosecant, secant, and cotangent, very well because they're what you need to type into the calculator. So the cosecant of x, its trig identity for reciprocal is 1 over sine x. And the secant is 1 over cosine. And the cotangent is 1 over tangent. So make sure you got those down. On the other side of that, like actually sine, cosine, and tangent can also be rewritten with their reciprocal value. It's less common that we would have ever done that before because like in our calculators we have a sine, cosine, and tangent button. But sine is 1 divided by the cosecant. So if you knew the cosecant, you could just do the reciprocal of cosecant and that would give you your sine. And so we'll have 1 over secant and 1 over cotangent. Now these 3 are going to start to show up in our work because we're going to have expressions where maybe we have cosecant in the bottom of a fraction, but we might be like, well, that would be really nice if we just had sine in the numerator. So we can switch out any cosecants we see in a denominator, we can rewrite as sines in the numerator. Okay, so we're going to be making substitutions. Okay, those are your reciprocal identities. Next up, we're going to talk about quotient identities, and these are a little less obvious. Okay, so we have 2 quotient identities. They are for tangent and cotangent only. So I don't have a quotient identity for sine, cosine, cosecant, secant. And before I just give you the quotient identity, I'm going to draw a picture so you can see why the quotient identity is what it is. This is a very similar picture we drew in Chapter 4. We're going to draw it in Chapter 5, and we're going to draw it in Chapter 6, and we may even draw it in Chapter 10. So this picture keeps coming back. Let's imagine this is the unit circle. What do you know about the unit circle? It has a lot of angles in it. What's always true about everything on the unit circle? The radius is 1. So I'm going to pick a point up here that is some xy ordered pair around the unit circle, and the radius to that point is 1. And we drew this picture last chapter, and we said, okay, so this is some x and some y. There's my x, there's my y. And then we started studying the unit circle, and we said, y is always what? Stone says the sine. So y is always the sine of theta. X is always cosine of theta. We decided that, right? X over r, y over r, but r was always 1, so cosine was always x, sine was always y. Okay, going back. Tangent, how do you normally do the tangent ratio with x, y, and r? y over x, but y is sine and x is cosine. That's our quotient identity. Every tangent can also be rewritten as sine x over cosine x. Maybe I want to rewrite it as 1 over cotangent. Maybe I want to write it with the quotient identity. I have to make that decision. I can now write it two ways. Okay. And then cotangent would just be cosine over sine. Okay, with that same picture, we can get the very first Pythagorean identity. So think about the Pythagorean theorem. In this picture, old way, which is like x, y, and the hypotenuse is 1, it would be x squared plus y squared equals 1 squared or 1. But now we know we could also say it's cosine squared plus sine squared equals 1. And I think I have mine written in swapped order, sine squared plus cosine squared equals 1. Either one is fine because addition is commutative. It doesn't matter which way you write the sine squared plus cosine squared. Okay. Now pay attention to how we're writing the squared trig functions. You put the square like sort of in between the trig function and the angle. You don't want to say sine of x squared because then you mean you're squaring the angle and then you're doing the sine. When what we're trying to say right here is this is like the sine of x times the sine of x. We're doing the sine of the angle and then we're squaring it. Okay, so that's how we write it. Okay, now something that you'll want to be on the lookout for, and this can be kind of hard for us in the beginning, because the Pythagorean identity has addition and subtraction in it, you can manipulate that equation. Like it doesn't always have to look like sine squared plus cosine squared. Do you agree with this? The sine squared of x is equal to 1 minus cosine squared. All I did was subtract cosine squared from both sides. Okay. And I could do it the other way. I could subtract sine squared from both sides. Okay. So all of the Pythagorean identities, I'm going to give you two more which are much harder to know, but you'll be responsible for those. But all three Pythagorean identities can be like manipulated. I call it manipulating the equation. You're just moving things around. Okay. And this can be really handy. So like if you're working on a problem and it looks like 1 minus sine squared x, then in place of 1 minus sine squared x, you can write cosine squared. It substitutes in for that expression. Okay, so we can replace it. Here are the other two Pythagorean identities. They're less obvious, in my drawing up there. So if we have time another day, we can talk about like why these two Pythagorean identities are what they are. But for right now, I'm going to say write them in your notebook. You are responsible for them. So we have 1 plus the tangent squared of x is equal to secant squared x. And 1 plus cotangent squared x is equal to cosecant squared x. These are a little bit harder to remember. It's easy to like forget which one is with the 1 and which one's on the other side, and what to pair up together. So like mark this in your notebook, highlight it, star it, circle it. You're going to have to spend some time with these to get familiar with them. Every year that I do trig identities, I just kind of have to relearn them. Okay? I don't always remember them exactly. These things can also be manipulated, right? So I could say that 1 is equal to cosecant squared x minus cotangent squared x. So I can also make that substitution, move the things around. Okay, the last identities are going to be even odd identities. The identities that I have given you so far, very important. You are responsible for knowing each and every one of them. The even odd identities I'm giving to you today because they may be on your homework, but you don't necessarily have to have them all memorized. Okay? They're called even odd identities because they go with whether your function is even or odd. So the first two groups that I'm giving to you are like families, sine and cosecant, and tangent and cotangent. And they actually both work the same way. If you do the sine of a negative x, so a negative angle, then it really is the negative or the opposite of the sine of the positive angle. So you can kind of think about it like bringing your negative outside. And it's true for sine, cosecant, tangent, and cotangent. They all work the same way. If you have a negative angle inside, you can sort of like bring out the negative. It's really just the negative trig ratio with a positive angle. The reason why these work, they're not even, they're odd. These are all odd functions. And so if you think back to chapter 1, semester 1, talked about odd and even functions. Odd functions are symmetric to the origin. And our algebraic test for odd functions was, does f of negative x equal negative f of x? Well, that's what's happening up here. Putting a negative x into the function, and you get the negative function value out. Cosine's not on that list because cosine isn't odd. It's not symmetric to the origin, it's symmetric to the y-axis, so it's even. Okay, so here's the rule for cosine. Be very careful when you're writing down cosine and secant. The rule changes. Notice that if you put a negative angle in, you just get out the positive cosine or positive secant. There's no negative left over.
So the only way to make it negative is if you were to just automatically have a negative in front of the cosine.
Yeah, you would have to like multiply it by a -1. This function is an even function. It's symmetric to the y-axis. And that test was, does f of negative x equal the original function? Remember, if we just did that one substitution with negative x, if we got the original function, we would say it's even. So it doesn't equal the negative, it equals the original. Okay, so these might show up on your homework. Like, it is possible that, like, somewhere there would be a cosine of negative x. And the thing here is just use the even odd function. Either it is a negative cosine x or a positive. Well, it's going to be positive, right? So you just have to decide whether it's an even or an odd function. Okay, we'll get to using our trig identities here in a little bit. Before we do that, I have a few other things to do. One of them is factoring a trig expression. Because this is going to be one of the things we can try when we're trying to go from one expression to another, just like when we're changing one word to a brand new word. Okay, here's the thing. Factoring a trig expression is the same as factoring a polynomial. Like, you have the same rules. If it's a trinomial, I do guess and check. If it had 4 terms, I could try factor by grouping. If it has two terms, I'm going to check for maybe like a greatest common factor, difference of perfect squares. I suppose there could be a sum or difference of cubes because those had two terms. And I can always look for greatest common factors. So this is a polynomial, right? Over here on the sideboard, x squared plus 5x plus 6. And you could factor it. What multiplies to give you x squared? X and x, so that would be your two first terms. What multiplies to give you 6? 2 and 3, or 6 and 1, but you have to choose the right one that gives you the middle term, which is obviously 2 and 3, right? So it's x plus 2, x plus 3. The difference with the trig expression is instead of having these x's there, there are going to be some trigs. So let me make it tangent squared x plus 5 tangent x plus 6. Then I could think about factoring it. Well, what would multiply to give me tangent squared? A tangent x times a tangent x. What will multiply to give me that 6? 2 and 3 to give me the 5 in the middle. So I'll put a plus 2 and a plus 3. When I re-multiply it out, I'll get the tangent squared. I'll get the 3 tangent x plus 2 tangent x is 5 tangent x. And 2 plus 3 is 6. Okay. It just, you gotta like think about it differently, right? Okay, so here are two that we're going to try to factor. So I've got 2 cosecant squared theta, and you're going to notice in the textbook they might change x's to thetas or alpha or beta. It doesn't matter what the variable is. Minus 7 cosecant theta plus 6. And then a different problem to try, sine squared theta minus cosine squared theta. So I'm going to give you some time right now. Can you factor either expression? What do you think?
It has to be two negatives because it's a positive number that's being multiplied with a negative number. Or that comes with add, you know? So you know, like the far right number is the number that's being multiplied. I'm bad at it when it has just the 2 in front of it. So I'm just being honest with you.
If you get really stuck when you're factoring a trig expression, maybe try like I did up here instead of like I put in trig expressions. You can always try taking out the trig part and making it just like an x squared or an x. If you have different trig ratios, then they would have to be different letters, like this one. Use an x and a y.
Okay, so it's going to be 2 cosecant theta minus 3 times cosecant theta minus 2. And then it'll be 2 cosecant theta squared. Yeah, that's right.
Okay, let's see what we can do. Your first term is 2 cosecant squared theta. So to get the cosecant squared theta, you obviously want a cosecant times a cosecant, but you'll have to put a 2 in front of one of them. Okay, very good. And then you can go to this back one. This is just a 6, right? What multiplies to make 6? 2 and 3, 1 and 6. But you got to choose correctly so you get your middle term that you want, right? Did anybody figure out which You want Brody? -1 and -6. Does it matter where I put them? -1, -6. So I'll get -12 and -1. -6, -1. So I'll get -6, no, -2 and -6. That's 8, right? -2 and -3. So I'm going to make this, you want this one a 3 and this one a -2. So then I'll have -4 and -3. Yeah, that'll give me my -7, won't it? And then I'll get a +6 and I'll have the 2 cosecant squared. So that's kind of like guess and check, just finding the ones that work. But remember, it has to actually make your middle term. Okay. Did anybody figure out sine squared minus cosine squared? What do you think it is, Nikki?
Sine theta minus cosine theta times sine theta plus
Sine theta minus cosine theta times sine theta plus cosine theta. Because then sine times sine is sine squared. Negative cosine times positive cosine is negative cosine squared. And this one would be positive sine cosine. And this one will be negative sine cosine. Does anybody remember what special factor pattern that is? A difference of perfect squares. Yeah, when one is minus and one is plus, but the two factors look exactly the same. So this is a difference of perfect squares. Okay. Good. Those you just gotta kind of get used to seeing them, right? And like if you're really, really struggling, like with this one, I could have rewritten it as like a 2x squared minus 7x plus 6 and tried factoring it with just x's, but then I would know my x's would be cosecant thetas. On this one, if I rewrote it, I could maybe say it's like an x squared minus a y squared. Like a sine and a cosine aren't the same unknown. So then how could I have an x squared minus y squared? Okay. These bullet points are super helpful. The number one rule on your homework tonight is try something. Like maybe on the word identities, you know, number 11, winter to summer. It's that person has 16 words up there. Some of us may have started and then got like lost or trapped, so we couldn't create another word, but we tried something. Early in this chapter, you have to do something so that when we go over stuff in class, you can find like little tips and tricks for yourself, connections to make going forward. But if you come with nothing done, everything that we do on the board for you and around the room, it doesn't really help you figure anything out because you haven't tried anything yet. So try something. When I come around tomorrow to look at your homework, there should be no blank problems. You should have like 2, 3, 4 steps for everything. You try. Okay. If you can get it all into one trig function, that might be something to try. Like if you notice that your expression has a bunch of tangents and cotangents, well, maybe change all the cotangents to tangents and things will cancel. So try to get it in one trig function. If you can't get it in one trig function, my favorite 2 trig functions to get it in is sine and cosine. That's one I use a lot. Let me just change everything to sine and cosine and see if it helps. It doesn't always help. Sometimes you do it too early and it gets really messy. but it's an option. Okay. If you notice that you can factor something, okay, so if you saw a difference of perfect squares, or maybe you see two things that are being added and subtracted and they share a trig ratio in common, so you can factor it out, try that. See what happens. And then the last one is combining fractions. When I say combining fractions, I really mean two things. Maybe you have fractions that are being multiplied, so multiply them. You know, maybe things will cancel out. Just multiply across on top, multiply across on bottom, right? The other option is adding, which is also subtracting. You will have to be really careful with this one because what has to be true in order to add and subtract fractions? You have to have a common denominator. Your things won't look like numerical fractions. They'll be fractions with trig ratios in them. So you just have to make sure that you got the same looking denominator so that you can do the rewrite. Okay, so here's my first example. This might be like some of your homework problems. It says cosecant x times secant x minus cotangent x. And really the directions in your homework or in the textbook, they're just going to say simplify the trig expression. What? What it's saying is this can be simplified into something much easier than 3 trig ratios. Okay. My suggestion to you, and I want you to do this on your quiz on Friday, is write out your reasons. Like every time you do something, say what you thought you were doing. Because it gets confusing for me. Sometimes people think they're doing a quotient identity or they think they're adding fractions and you're not. But by writing out those reasons, we can kind of like tell what we thought we were doing. Okay. Well, I don't think I can actually subtract these things. Don't know anything about that. And then the two terms that are being subtracted, they really don't have anything in common, right? Like they both don't have cosecant or they both don't have secant, so I can't factor anything out. So what do you think you might want to do? Try, what's that? Changing it to sines and cosines. Yeah, what are we going to use to do that? Reciprocal identities. Okay, so we'll say cosecant is really 1 over sine. And secant is really 1 over cosine. Cotangent. 1 over tangent, which we could write it for reciprocal identity, but then that doesn't do what Lexi said, which was write it all in sines and cosines. Is there something we can do for cotangent? Do cosine over sine. So I'm going to say in my reasons here, I have a mix of things. I have reciprocal and quotient identities. Okay. All right, so now everything's in sines and cosines. What do you want to do next? Okay, make everything have the same denominator. Because aren't you subtracting two things? Okay, and this one over here we're multiplying, but that's just going to be like 1 over cosine sine. Okay, so we'll kind of include that multiply step in here. So this one is 1 over sine x cosine x. And then Stone said get common denominator, so this one needs a cosine. So I multiply cosine in the denominator, then I have to multiply cosine in the numerator, so that becomes cosine squared x over sine x cosine x. And I could say, like, for that step, I did multiply, okay, and then I did do common denominators. So I kind of did two things in one. Now, before I do any other steps, does anybody need any part of that clarified, like why we did what we did? Mm-hmm.
Why didn't you just write like cosine? Because can you multiply cosine by 1 and sine by 1 and then like cross multiply?
Here?
Like up sine and cosine is 1 over sine and 1 over cosine. Can't you cross multiply there?
No, you can only cross multiply over an equal sign. This is just multiply. So you multiply across on top to get 1, and you multiply across on bottom to get sine and cosine. Okay, so now you got common denominators. You can subtract 1 minus cosine squared. And then keep my denominator sine x cosine x. So I'm going to say my reason here is subtracting. I'll move, hang on. So I subtracted. You cannot cancel cosine because this cosine has a minus in front of it. So like you can only cancel things when they're factors, and that would mean like everything's being multiplied on the top and the bottom. Then I could start canceling cosines. So that's a really good one, but no, we can't cancel cosine as is because it has 1 minus cosine squared. 1 minus cosine squared. Does that sound familiar? That is the Pythagorean identity. 1 minus cosine squared is equal to sine squared. It's the manipulated Pythagorean identity. So we can make the substitution. 1 minus cosine squared is sine squared. So we have sine squared x over sine x cosine x. Move this up. And then I'm going to write my reason as my Pythagorean identity. And I'll write out, we wrote down sine squared x plus cosine squared x equals 1. That was the original Pythagorean identity. But remember, we solved that. We manipulated that. We could subtract cosine squared from both sides. So sine squared x is equal to 1 minus cosine squared x. Meaning wherever I saw that 1 minus cosine squared, I could replace it with a sine squared. That's super handy. So when you see squareds and ones or different squared functions, I always kind of try to think back to my Pythagoreans. Okay? Don't use Pythagorean identity if it's not squared. Okay? But if it's being squared, I might look to see if there is a Pythagorean identity. Okay, and then Stone said factor, but really we're just canceling stuff, right? It is now all factors. We have sine times sine in the numerator, and we have sine times cosine. So we don't have the plus or minus anymore. So we can cancel out sine in the denominator, and for this I'll just cancel out one of the signs, right? So now I have sine x over cosine x. My reason there would be like cancel or simplify. And then that's a quotient. Yeah. Yeah. That's our quotient identity. So that stuff that I had up at the top, what was it, like cosecant x times secant x minus cotangent x? Who would want to do all that? You're really just doing your tangent x. Now, this is a really important skill for calculus. Like right now, we're just going to be practicing like doing the substitutions and the rewritings. But in calculus, you need this so that you can do integrals and derivatives way easier, right? Like you don't want to do the one that I gave you. You want to do just the tangent x. Okay, so trig identities are super important when you get there. Okay, I have one last example that I want to go through. And it's the trig substitution. So you may have some problems on your homework like this. The directions will read the same way. It says something about like write the algebraic expression as a trig function of theta, where theta is between 0 and pi halves. The problems will look like what I have here on the screen. So like you see this, a lot of them will have a square root in them. It doesn't look anything trig. It just looks like algebra stuff, right? 25 minus x squared. But then they'll tell you what x or some other variable is in trig form. So x is really 5 times sine theta. So I call this trig substitution because I'm going to make a substitution right away, right? Where I see x, I'm going to write 5 sine theta. So this is really the square root of 25 minus, and I'm going to protect it with parentheses, 5 times sine theta quantity squared, because I'm squaring all of x. So that's really saying like 5 sine theta times 5 sine theta, which is 25 sine squared. Because I would square the 5 and I would square the sine. It's multiplying all by itself. Okay, here's where you got to be really careful. You can't square root. That is not 5 minus 5 sine theta. Because we don't have a property for square rooting when there's plus or minus. Okay. So what you would really want to do is both of these terms have a 25 in it, right? I can factor out the 25. So that I have 1 minus sine squared theta. And this will help build your confidence with Pythagorean identities. 1 minus sine squared theta is really cosine squared theta. And you might be using the other Pythagorean identities on these problems. This is 25 cosine squared theta. Now, can I square root? Yeah, because I don't have plus or minus anymore. So the square root of 25 is 5, and the square root of cosine squared is cosine. Okay, but that's going to help kind of build some of those Pythagorean identities that you recognize them better, because that's one of the trickier things in the early chapter. Okay. Your homework gold sheet is just a little bit different than it's been in the past. Instead of having a column for homework and optional extra practice, it has all the problems together. So down at the bottom it says the bolded and underlined is required. So that's like your normal homework, and if you want extra practice, you can do the non-bold.
Oh, shoot. You're